Before we hand this over to my colleague Laura to start us off, I want to do some very important work here. I want to acknowledge that we are on the traditional ancestral lands of the Ute, Arapaho, and Cheyenne peoples, whose rich cultural heritage continues to shape this region. We honor their deep-rooted traditions, including skilled textile practices, which embody stories, spiritual beliefs, and communal knowledge passed down through generations. The intricate beadwork, weaving, and garment making of these indigenous communities reflects a profound connection to the land and their resilience as artisans and storytellers. We commit to respecting and learning from these enduring traditions as we acknowledge the history and presence of indigenous peoples here in Boulder, Colorado, and the Front Range region. All right, so you guys all here today joining us, handing over the ropes to my colleague, Laura Devendorf, for some announcements.
Cool. Sorry about that. Just having a little bit of trouble with the interface. So yeah, hi everybody. Thank you so much for joining us. Thank you also to my class who's live in person at this event, and eventually I'll turn the camera around and maybe you'll get to see them for those of us in the class. It's that little thing that's been spying on you in the back of the class. Just kidding, it's not on all the time. But this series has been brought to you by the Unstable Design Lab, which is a research lab at the University of Colorado in the Atlas Institute. I just wanted to maybe do a quick plug for some of our other research and programs, which span kind of interaction design, weaving, and some newer research on sustainable materials. One of the programs that we're really focusing on this year is called AdaCAD, which is an open source and free drafting software that's available online. So yeah, if you have a moment or you're curious, feel free to jump over to docs.adacad.org and play around. I also wanted to give a plug to our YouTube archive. So every talk that we've hosted in the series so far, and we've done the series for the past 2 years, has been hosted on YouTube. And these have been really great resources I've heard from other people in the community. One for just watching for your enjoyment, but also for integrating into different curriculum and hearing the nitty-gritty a little bit more about different weavers' practices. But without further ado, I'm really excited to welcome Katya Arquilla as our experimental weaving talk series, opening talk. Katya is a professor also here at CU Boulder, who I had the pleasure of collaborating with when she was a PhD student. So when we ran our first experimental weaving residency, Katya was the most serendipitous and lovely collaborator who came in and worked with our weaver in residence to kind of explore different structures for on-body sensing. And in the past, we've really focused this talk series on weavers, and Katya actually represents the first time we're bringing in someone maybe who's coming into weaving adjacently, but I'm hoping that learning a bit more about their research and their practice and the domains in which weaving can make a strong impact in science and engineering will be interesting for this community. So without further ado, let's go ahead and welcome Katya. Katya, I'll let you take it over and share your screen. Because Zoom is a strange, cold universe, much like outer space, maybe just say a quick hello to Katya in the chat. Let her know you're here. And yeah, and we'll go ahead and get started.
Awesome. Thank you, Laura. Just checking everyone can see my screen and can hear me okay. Cool. Yeah, I'm really excited to be here. It's a lot of my PhD work was done in Laura's lab, in the Unstable Design Lab, and that experience was really mind-opening for what can be possible with textiles, especially as they can be applied to different parts of the engineering world. So today I'm going to talk to you about the role of experimental weaving in bioastronautics. And as Laura said, I'm not a weaver, I'm an engineer. I'm an assistant professor in aerospace engineering sciences in a lab called the Bioastronautics lab. And so really my training is all in engineering, and I was lucky enough to get the chance to learn, just scraping the surface of weaving and understand enough to be able to apply some of the principles to on-body sensing, as Laura mentioned. Um, first, I'll start by just talking about what is bioastronautics. So we define it as the study and support of life in space and other complex high-stress environments. So with spaceflight, we have people functioning at a very high level, usually very fit people, very high cognitive function in an environment that is dangerous and challenging in many, many ways. So the research that we do spans everything from developing spacesuits that make them able to function outside of the vehicle, testing their vestibular system in things like centrifuges, and then developing life support systems as well that can produce oxygen for that environment. So really a broad swath of research interests, but all focused around this idea of supporting humans in these complex high-stress environments. And so, as I mentioned, it's really a diverse range of research topics, everything from habitat design to behavioral health, which is something my research has focused on quite a bit. And we're constantly expanding our research methodologies to meet the needs of the challenges that we study. And so we're constantly looking at new ways to monitor things like human health and performance in these environments. And we pull from a lot of different disciplines to be able to develop creative solutions to these challenges. And this is really where experimental weaving comes in. It's yet another potentially really different method than everything else we use that has opened up the design space for how we do this monitoring of human health and performance. So the focus of the talk today, I'll talk a little bit about my experience doing research on developing textile electrodes for cardiac monitoring, which was the work that I did during my PhD in collaboration with Laura and the artist in residence, Sandra Virtanen. And I'll talk a little bit about how important it is to collaborate with craftspeople, like collaborations between craftspeople and engineers, and then how to experimentally validate wearable sensor performance and then down select designs, which I think is really the kind of structure that engineering brings into that process. Then I'll talk about some of the current advances in wearable sensing, so things that my students have been working on or are working on now, things like adjusting designs for different body types, and then how to deal with things like the sweat problem or the introduction of moisture into that skin electrode interface. And then I'll finish out by talking about other opportunities for experimental weaving in bioastronautics, things like spacesuits, radiation protection, and even habitat design and space architecture. So I think a good place to start when thinking about the physiological sensing side of things is to just talk about the physical and psychological challenges that come up in bioastronautics. And I have this table here that separates out physical challenges, psychological challenges, and then in space and air, because we talk about space flight and also aircraft quite a bit in bioastronautics. So on the physical side for space, probably a lot of you already know this, but space is a pretty weird environment. Being in microgravity does strange things to your body because your body was developed in 1G. So when you take away that gravitational force, you get muscle atrophy because you're no longer working to keep yourself upright. You get bone loss. Depending on the environment, you can have potentially toxic levels of carbon dioxide in the habitat that can affect your cognitive function. You can get decompression sickness if you don't go through the proper pre-breathe protocols before you go out on an extravehicular activity or EVA or spacewalk. Then there are also psychological challenges that sometimes couple with the physical challenges where these are high-performing individuals conducting many, many tasks every day, and that can lead to cognitive overload or chronic stress. And then in long duration exploration missions, we do worry about depression, anxiety, and negative team dynamics. If you have a small crew of maybe 4 people going to Mars on a multi-year mission, you're only interacting with those people for that entire time. There's high potential for conflict and negative team dynamics, which then can cycle back and affect you physically as well. In aircraft, we worry about things like gravity-induced loss of consciousness or GLOC, where you basically aren't getting enough oxygen to your brain. Hypoxia as well, where you're not getting enough oxygen. And then the same like cognitive overload, stress, and fatigue are known issues for aircraft pilots as well. And the picture on the right is an example of a crew that had they call it a mutiny, but basically they were overworked during their mission and decided to take a day off and cut their communications with mission control. That something like that could be catastrophic if there were an emergency. So behavioral health is something that we want to monitor and make sure that we're keeping tabs on for space missions. So for each of these areas, and I was worried my animations were not good, and we'll just ignore the arrow in the middle there. There are different manifestations of a lot of these issues in the human body, and we can use different monitoring methods to keep track of these. So things like eye tracking or cardiac monitoring can be used to track something like heat exhaustion during an EVA, or any of the psychological challenges can sometimes be tracked using cardiac monitoring. Similarly, with things like muscle atrophy, electromyography collects electrical information from your muscles activating. And so you can see if a muscle is not being used, you could monitor that using an on-body EMG sensor, electromyography sensor. They've also been used for psychological monitoring because you can actually collect muscle information about the forehead to get your expression. So if you're constantly frowning, you can see that on an EMG sensor, which is pretty cool. Sweat monitoring has been used kind of all over the place for psychological monitoring, things like cognitive workload. It's also potentially useful for spatial disorientation, so losing track of what's up and down, and that can lead to space motion sickness, which can be really treacherous. If you were to vomit in a spacesuit, you would basically die. It's pretty difficult to keep the vomit away from your mouth and keep you from breathing it in. Okay, that's enough vomit talk for this time of day. But sweat monitoring can be used for many, many different things. Same with respiration monitoring. You can use that to understand if someone's like panting quite a lot, it might mean they're not getting enough oxygen. And it can also be used to track psychological changes as well. So the point there is that there are all of these physical and psychological challenges that we can potentially track using different physiological changes that actually manifest at the skin. And this kind of suite of response measurements are called psychophysiological responses. And they're really one way to monitor behavioral health that's potentially unobtrusive and more objective than asking someone in a survey how they're feeling. So this comes out of basically the two parts of the autonomic nervous system. The parasympathetic division is what's controlling your ordinary body processes that you're really not aware of as they happen, like your digestion. But then the sympathetic division is things like the fight or flight response, which can lead to pupil dilation. So these are things where if you're startled or stressed, there are changes that manifest as like an increase in heart rate, increase in sweat activation, pupil dilation, that kind of thing. And we can measure those to connect them to your behavioral health. So psychophysiology is sort of defined as the connection between these physiological signals and your psychological state. And they're really these subconscious reactions to stimuli that you can track through their manifestation in your physiology. And there are many examples of these types of signals. Some are referred to as neurophysiology as well, like electroencephalography. EEG is measuring your brain waves. So that's sometimes referred to as neurophysiology. And then on the psychophysiology side, there are things like electrocardiogram, which is the electrical activity of your heart, electrodermal activity, which is your sweat gland activation, not even just the level of sweat, but actually the activation of the glands before you start sweating, which is kind of interesting. Electromyography, EMG, which is that muscle activation I mentioned earlier, and then photoplethysmography, which is a light-based sensor that can give you pulse rate as well. For my PhD work, I focused in on the ECG signal because it's really rich. It can be used to detect physical and psychological stress. And so that's why we decided to focus on ECG for the development of this first round of textile electrodes. And so if you're not familiar, this is what the ECG signal looks like. Each of these waveforms represents one heartbeat, and each of the different peaks, there's the P, Q, R, S, and T peaks. Each of those is produced by a different mechanism within your heart activating. And so you can see the strongest peak is the R peak. Most of the metrics that we talk about for heart rate variability are derived from this interval between our peaks, so the time between beats. The ECG signal is very useful, but is difficult to collect in operational environments because traditional physiological sensors have been bulky or single use and uncomfortable. If any of you have ever been prescribed a Holter monitor for long-term monitoring, usually a doctor will have a patient wear this for 30 days straight, and it'll be adhesive electrodes that you can't take off, and it can be quite uncomfortable. And it's also quite a bulky system that makes it difficult to perform normal activities. That's the real benefit of wearable sensors. They can be more unobtrusive, they can be more comfortable, and potentially non-stigmatizing. So if you're walking around with a Holter monitor on, probably people can see it and know that you have it on. The idea with wearable sensors is that you're integrating into a wearable form factor that's less obvious. There are many commercial off-the-shelf systems. Probably many of you are wearing a wrist-mounted sensor at the moment that has a PPG sensor in it that's detecting your pulse rate. But they come with challenges as well. They're subject to motion artifacts. If you've ever, gone for a pretty vigorous run and looked at the heart rate measurement, it can be kind of all over the place, especially if you don't have it very, very tight on your wrist. And they often don't provide access to the raw data. I know that I have a Garmin and it doesn't let me go in and look at my pulse rate. It just gives me like an average heart rate, which is very annoying. They're also usually wrist mounted, which means it's difficult to get ECG. Usually you need multiple leads to get the ECG signal. And the wrist mounted form factor means that you're usually getting PPG, so just pulse rate from this light-based sensor that you can see on the right here in the Empatica E3. So all this is to say that integrating electrodes into garments can solve a lot of these challenges, hopefully, and that was kind of the motivating factor for this work. Just going to check the time so I know I can't see the time anywhere. Okay, cool. So when we think about traditional electrodes versus textile electrodes, which we were trying to design, traditional electrodes usually have a silver chloride disc that's mounted on an adhesive patch. That's what you see on the left here. And you can see when you pull it off the skin, the adhesive is quite strong, so you do get like marks left on the skin and potential discomfort from that. They often use a conductive gel for skin contact, and that gel can dry over time, which changes signal quality if you're monitoring for long durations. And often a conductive goo or gel is added to decrease the impedance at the contact point, which makes the signals really good for short-term monitoring, but can cause challenges for long-term monitoring when you might get changes in the water content over time. And they're also consumable, so you can only use them once, which is a big problem for spaceflight. If we want to monitor people continuously for a 3-year mission, that's like thousands and thousands of electrodes, which when you think about launch mass, that increases your mass quite a bit, and then the cost of the mission quite a bit. And nobody's really going to pay for that many electrodes to go up. So it's desirable to come up with reusable solutions. So with textile electrodes, they're in this family of dry electrodes where there's no conductive gel. They're potentially better for long-term monitoring because you avoid that gel drying problem. But they are often susceptible to motion artifacts. So that's something you have to think about. If you think about, the shirt you're wearing now, as you move, the fabric slips across your skin, and that can create motion artifacts in the data. So noise in the data caused by that loss of contact. So you have to think of creative methods to deal with that. But they can also be reused. So you can potentially wear these sensors, wash them, and then reuse them instead of having to take new consumable systems with you all the time. So the way that we went about developing these textile electrodes was to use textile fabrication methods with novel materials. And I know there are probably many more novel materials than these at this point, but this was our starting point, using sewing and then weaving with silver-coated and steel-spun conductive threads, which you can see on the right, with the goal to develop electrodes that had the look and feel of clothing so that we could improve comfort, adherence, so actually make people want to use the system, and eventually increase the total amount of data collected. So this is probably more familiar to most of you than it is to me, to be honest, but we developed the electrodes on the TC2 automated loom that's in the Unstable Design Lab. And it's such a cool system, really. Like each of the 1,320 warp yarns can be controlled individually, and you get to develop this pattern and then have it like manifest on this device and develop a textile that matches the like bitmap that you created, which is just a very cool piece of equipment. It gives you freedom in textile shape and structure and different layers. And so here's just some photos of me developing the textile electrodes with my, very rudimentary skills, but I just thought it was a very free development platform where you really have this opportunity to try out different patterns and get that iterative design process very quickly, which you don't often see in engineering. So we ended up developing electrodes that were of 8 different sizes with 4 different patterns that were trading off basically the amount of thread anchoring in each of the electrodes and the contact area. So the idea was that if the thread was more anchored, you would get fewer motion artifacts because there would be less internal movement within the electrode. But if you anchored too much, you would lose contact area because you would have non-conductive threads in contact with the skin. And for the experiment to test the efficacy of these systems, we had 10 participants, all of whom were male, and I can explain that more if folks are interested, and seated during the experiment. We tested it integrated with a BioPack MP160, which is a gold standard physiological data collection device that we use in our labs pretty often. And so when thinking about testing, it's really important to establish those independent and dependent variables clearly from the outset. So for this experiment, we were thinking about the change in signal quality due to the size of the electrodes, the patterns that we were using to weave them, and the material that was being used. But we needed to be able to isolate each of those things in our experimental data. So that led to having 4 different patterns with each of the 2 types of threads in each pattern, and then each pattern in every size, so that we could look at differences in each of those metrics without any confounding factors between them, which leads to quite a few electrodes to investigate, like not that many options. So you get this kind of small slice of the design space, but you get a really good idea of how those changes work. And our dependent variables were signal quality and then comfort. So we developed metrics to assess signal quality, which I'll talk more about in a minute, and then also ask participants about the comfort of the system. And you really just need these dependent variables to be as quantifiable as possible, especially when you're doing this sort of exploratory study for what's possible with the technology. It's really important that you have like hard data to be able to explain really clearly what the differences are. We also had to think about the number of samples we needed to be able to see these differences. And so that involved a power analysis to look at what % change we would be able to see with the number of participants we had, how to handle inter-individual variability, which I will talk more about in a minute as well, and then testing within participants. So testing every single type of electrode on one individual. So each of the 10 participants saw every test condition so that we didn't let that inter-individual variability play into the results that we were seeing. And we also had to think about test duration. Ideally we'd have someone wear each of these systems all day and see what happened, but timing of that is impossible. Paying that many participants is financially infeasible. So we down selected to 2 minutes with each electrode. And that's really just a trade-off of balancing how much data you can get with test fatigue. It's difficult to get people to participate in a test for more than an hour or 2, especially when you're like just putting different things on them and they just have to sit there like getting their ECG data taken. For the test procedure, we had all of the participants seated during the experiment. This first iteration wasn't really designed to handle motion very well. That was in a later iteration that I will also talk about. So they were all seated during the experiment. And we really had to ensure that the procedure was really clear and that it was a controlled environment. And that even included facing the participants so they were not looking at their own data, because if you if you're sitting there and you see your ECG data start coming in, you will do things to change your ECG signal, or you'll think, oh, that's a little high. Maybe I should like take some deep breaths and lower it and things like that. So we didn't want that kind of feedback and interference. So we took it down to that level of really controlling the experiment. And we also got IRB approval from the university, which is required for this type of participant testing. So in thinking about the analysis, what we really wanted to see was how are we going to know if one of these electrodes is different than the others, or if one is better or worse? And that came back to the question of quantifying performance. We ended up doing this using peak detection. So, if we want this system to be a valuable wearable system for an operational environment, we need to be able to identify the different peaks within the ECG signal. And so we did this visually and then with an automated algorithm and basically compared the difference, because visual inspection is still the gold standard for identifying peaks within the ECG signal. So we figured if the automated algorithm is identifying these correctly, then the sensors are working pretty well and they're not getting so much noise that they're obscuring the data. And we also took comfort surveys, seeing if the electrodes are actually more comfortable than their traditional counterparts. And then we looked for noise as well and quantified how much noise we were seeing in the signal, because noise can lead to misses, so not being able to see the peaks and identifying them correctly, as you can see on the right, or false positives, so seeing like large features in the data and thinking it's an R peak when it's not actually. So some of the performance metrics we developed, I'll just talk through and then we'll talk through some results. But as I mentioned, we were comparing this automated peak detection with visual inspection, and we measured precision. So that's the fraction of detected peaks that are actual peaks. So basically correct hits. So it's the number of hits. So correct peaks identified over the hits plus false alarms, if it was detecting things as peaks that weren't actually. And then recall, which is the fraction of the peaks in the signal that are successfully retrieved, which is the number of hits over the number of hits plus misses. So that's the number of correctly detected peaks over the total number of actual peaks. And then use that to create an F1 metric, which is commonly used for this type of assessment, which is just the harmonic mean of the precision and recall. And so I'll show you a few things not working. Okay. I'll show you a few violin plots to talk about the results, and the structure of them will be the same. So I'll just walk you through the structure so that it makes sense when you see the next results plots. But basically on the x-axis, we have each of the components of the ECG signal. So the R, P, Q, S, and T peaks, and then 0 to 1 on the y-axis for the precision and recall measurements. And then you'll see the median value is the dot in these violin plots. The interquartile range is the thick black line, and then the distribution of the scores is that like gray area on the outside. So from our results, I'll say now they were fairly mixed, which is common in my world of research. Is mixed results. It's sort of par for the course. We found that the electrodes that were larger than size 5 of the 8 showed the highest precision, recall, and F1 metrics for the R, P, and S peaks. So you can see that here the R peak is pretty well detected, and these results are for the size 6 electrode, which is about 7 by 7 centimeters. And you can see also that there's quite a bit of variability in the P and the T peaks. But we expected to see a decrement with the largest sizes, where we were expecting a lot more movement in the fabric, basically, that would create motion artifacts. And we actually didn't see that decrement in the largest sizes, which makes me think that we could have gone a fair bit bigger and still been able to get pretty high quality signals. So maybe our small sizes were too small, and our large sizes weren't quite large enough. For the pattern results, we found that the twill pattern performed the best. So you can see the results here. This is an example. I think actually this is across all participants for the twill pattern. You can see that the R peak is very well detected from the automated peak detection algorithm, as is the S peak. Again, there's struggle with the Q peak, because if you look back here, like that's the tiniest peak and it's right next to a pretty large peak. So automating the detection of that is a challenge in general. So you can see that here. But we also saw that there was very high inter-individual variability, which you can see here in the comparison between participant 9 and participant 10. You can see that the Q peak detection is poor for both, so we're accepting that result. And then the performance here is much more dependent upon the individual than the type of electrode. So this is their F1 metric across all electrodes for participant 9 and across all electrodes for participant 10. And you can see that for participant 9, most of the peaks except the Q peak were very well detected, and that distribution is pretty tight around that high value for the F1 metric, where it's really the opposite for participant 10. Their best median score is like 0.8 for the R peak, which is the most prominent peak. And you see these really wide distributions. So the takeaway here is that there's a lot more happening between the electrode and the human that we need to understand to be able to hone in on high performance for this type of system. So in talking about the challenges of inter-individual variability, body type is a big factor. So the type of tissue that you have on your chest affects your skin contact during motion. Breast tissue can also be really challenging for chest-mounted sensors because you get these concave regions that you get like gaping of the fabric over those. So that can be a challenge. And you also, my controls are, hello, okay. Skin type is also really challenging. Some people just have sweaty skin or a propensity to sweat, and that can affect signal quality. It's likely that participant 9 that you saw that had high performance just had sort of dewy, sweaty skin, or they like use a lot of moisturizer, and we don't really know. The presence of hair can also reduce contact, and the type of hair can reduce contact as well, especially like curly hair can actually push fabrics away from your body. So that's something to think about as well. And we've done some follow-on and then active projects to address both of these challenges. So for the body type challenge, this work was done primarily by Ella Schaus, who is another student in the group that I worked in with Ali Anderson, now Heyman. And we looked at adjusting the designs based on body type. And so this system, it's called Argonaut, and it was designed for individuals with breast tissue. And Ella actually added foam inserts to increase skin contact so that the electrodes would actually push into the body instead of kind of sitting passively on the chest. And so you can see that here, these are the same electrodes that I tested, but with a foam insert on the back that made them push into the skin. And then all of the electronics for the system were also embedded in the garment, but they were removable for laundering. So they were all sewn into this zippable pouch so that the human wasn't actually physically interacting with the electronics, but they were completely removable so that the garment could be reused, which is pretty cool. I think one missing piece of this design is that these woven electrodes were stitched into a garment, which creates stitching around the electrode. Stitching can lead to irritation of the skin. So I think a future question, a future area for work is, could this garment have been completely woven, or could it have been better integrated so there were fewer interfaces to deal with for the human? And maybe it could look even more integrated so that when the human takes it off, they don't see these like 3 electrodes staring back at them, and it feels more like a normal garment. We're also now working on designing sensors to manage moisture. So I have a visiting scholar with me this semester, Josep, who's been working on how to deal with the sweat problem. Because we know that sweat can impact signal quality, and we can't always predict how it's going to impact signal quality. So he's been looking at designing electrodes to remove sweat from the skin interface. We're not removing anyone's skin. He's been looking at hydrophilic and hydrophobic properties of different materials so that you can potentially get sweat to move through a first layer and then be basically rejected from the sensor, which is what you see on the bottom, or potentially use capillary forces to move fluid. So having channels through the sensing area where sweat will basically, under capillary action, move from the inside of the channel to the outside of the sensor and get wicked away. Still very early stages with this, but something we're thinking about and working on. Some of the challenges that I'll mention are, pushing into development before there's enough design iteration. This is something that I definitely struggled with. Like, all of the sensors I designed were squares. And as you can see on the right, that's not a square. And part of that is, not having enough time and really enough design iterations to be able to work enough with the loom so that I was making squares instead of rectangles. And at some point we decided, this was good enough, but I think it's a very clear indicator that these things need to be an iterative process. There's also this balance of the breadth of the study with the complexity of the experiment. As I mentioned before, like, each new thread you add means you have to test another like 8 to 12 electrodes. So can you really afford to like add that thread, or do you need to do a follow-on study? And then being really intentional with garment integration. So thinking about functionality versus comfort and really the goals of the system at the end of the day. And then there's always this tension that we have between creativity and function. Engineering problems in human spaceflight require creativity to develop unique solutions, but creativity often gets stifled with this emphasis on function, because we like things that work. And so we keep using the things that work because we know they work. And this is very clear if you look at, the Apollo spacesuits on the left and then the ISS spacesuits on the right. They look extremely similar, right? Because we knew that they worked and we kept iterating in small ways on these systems. I think that's changing now with the upcoming challenges of human spaceflight, but it's always difficult to work within that tension of, trying to go with technologies that have been proven and are known to work well, and then giving enough space for creative solutions to be integrated. And really the way to get around this is through reporting the process for each of those design decisions very clearly. So if it's a trade study, making the results of that trade study available, and then that quantification of performance for novel wearable systems, especially being able to quantify why something is better so that you can make a clear argument as to why it should be used. And then I'll take a minute to just talk about the importance of meaningful collaboration. So as Laura mentioned, I got to work with the first artist in residence for I can't remember the name of the program, the Weaving Artist in Residence. I got to work with her very closely, and it was amazing, to be able to tell someone what the kind of functionality I was hoping for in a material, and then see it created like the next day, and be able to go back and forth and have that meaningful discussion around what the possibilities of the fabric could be and what the needs could be, and then identifying areas where we didn't even necessarily think ahead of time that this would have been feasible with a fabric. Like on the right here, this is an Arduino and all the wiring just in a fabric with foam padding around it, so someone could wear it and not know that they had it on, which I thought was amazing. And really stressing here that it's important to include craftspeople as technical collaborators, so that you can really reveal the breadth of that design space and allow for those creative solutions. And then couple that with rigorous analysis, which I mentioned is really the only path to implementation for novel technologies. And you can really characterize the limits of the design, and that really supports iterative design. So if you analyze a certain property and are able to give that property a number, then you can compare the next iteration to that. And I would encourage all of you to read the paper that Laura wrote on this, Craftspeople as Technical Collaborators, Lessons Learned Through an Experimental Weaving Residency. It's a great paper about this whole process. So now just to wrap up, I'll go through some other applications of textiles in bioastronautics to get all of you more expert weavers than myself thinking about these things. So spacesuits are a huge one. There are a lot of soft goods in the spacesuit, including a cooling system, radiation, and I'll talk more about spacesuits in a second. There's also radiation protection, where I know a collaborator of mine, Svetlana Borskina, has been working on polyethylene fibers that are actually extruded polyethylene that can be integrated into garments and potentially could be used to protect people from radiation in their clothing. And there's also habitat design and space architecture applications that I'll talk about a little bit more too, where you can look at the inner habitat walls as an opportunity for interaction with the crew and an impact on the experience of the crew. And that can be a place for interactive textiles as well. So on the spacesuit side, spacesuits are made up of many layers, and you can see a diagram on the right of a mechanical counterpressure spacesuit. They have a cooling garment, as I mentioned. There's a tear-resistant layer. There are insulation layers, and I think there's really room for improvement in all of those areas in terms of novel textiles. And there are also more novel mechanical counterpressure spacesuit designs, or MCP suit designs, that use compression around the body to maintain pressure instead of this kind of balloon concept that we use now. And it's really challenging in areas that are not simple cylinders, so like the armpits, knees, elbows, and things like that. And I have seen many amazing three-dimensional woven structures, and I just have to imagine that there is somewhere in there that it's going to be possible to better shape this type of mechanical counterpressure suit using all the capabilities of weaving and knitting. So yeah, I think there are big opportunities here for novel textiles that can help increase mobility and eventually our capability to explore in these suits. For habitat design, I actually have a student, Lynn, working on this right now. I'll explain more about their project, but space exploration requires living and working in an extreme, isolated, confined, extreme, or ice environment where your habitat becomes really essential to your experience because you can't go outside as a behavioral health countermeasure. So we can think about habitat design and space architecture as an influence on behavioral health and potentially use that to our advantage. So the way the different areas of the habitat are used can be indicative of team dynamics, and giving people the opportunity for agency and placemaking in the habitat could be really important for behavioral health, especially on long duration missions when you're in a really tiny spacecraft. So Mish is working on studying the connections between space architecture and behavioral health. And they developed this folded textile for adaptable sound insulation, which the idea is that they're actually taking this system to Scotland on Sunday to test expanding these panels in each part of this tent, and then being able to stuff locally sourced wool into each of the folds to provide additional sound insulation, and then channeling external sound into the habitat, and just seeing how this kind of modulation of the environment can help with behavioral health when you're living in an ice environment. So very cool work. And this is not something that we wove ourselves. And I think that there's a lot of opportunity there as well for three-dimensional woven structures that can be used in this like interactive way with the habitat. So yeah, that's all I have as my talk, and I'm happy to take any questions. If you're interested in bioastronautics, there's the webpage. You can see our current project, students, and faculty. And then if you're interested, I'm happy for you to reach out to my CU email. But thank you very much.
Oh my gosh, that was so awesome.
We
I'm
can
so
clap in
excited.
our class. Yeah, go ahead, Stephen.
Oh yes, we do have a couple. We have a great technical question here in the chat. If you want to check that out, Katya. But I also wanted to just ask you just a few questions too, relating specifically to the end of your lecture. I think well, I actually do. I want to know more about these habitat designs for behavioral health, but I think that's just for myself. The real question that I have for you is we have some designers and some artists here in the chat, and I think the perspective for you is like we need to integrate these people into our engineering process. What sort of advice would you have for those people, artists and designers who want to get closely involved into something like astrophysics or into aerospace? How do they find these collaborators outside of a university, or what would be good ways for these folks to approach scientists and as a collaborator?
Yeah, that's a great question, and I'm by no means an expert, but my first thoughts are that universities are kind of one of the only places where things like this happen right now. So the university environment is conducive to collaboration and taking the time to explore new things. And so that's they're a nice anchor point for starting collaborations like this. That's certainly how it has worked for me. And then I think finding a good collaborator is really important. Like, I think none of this work would have been possible for me. And like, you know, part of my research portfolio now is growing in this direction because I talked to Laura and Laura knew how to integrate with this community. So I think those like personal connections and putting real time and effort into those connections is the best way to do things. Like I really strove to integrate myself into Laura's lab and spent a lot of time there and tried to, you know, leave any preconceived notion of what to expect before I went and really tried to just immerse myself. And I think that like open-mindedness and like willingness to just be immersed is really important.
Yeah, thank you so much. Of course, it was wonderful to have you in the lab and so excited that you're now here at CU Boulder. So we get to collaborate more and more. It's so exciting.
Yeah, I get to
And
come back.
yes, I know that prototype that you helped make is like one of my favorite objects that's in the lab. It's wonderful. We've another question back here. It's a little bit more of an engineering question. I don't know if you want to check it out. It's there in the chat, Katya, but it basically, there could be several sources of inner individual variability. You covered a few. How can one control of the inner individual motion? How can one control for an inner individual motion? One subject can move more and another subject moves less, but movement variability will affect the 5 EKG readouts. That's a great question about. I loved all your insights about how individuals were so influential in these results.
Yeah, for sure. This is a great question. And it's something we struggle with all of our research is that humans are incredibly complex and incredibly different from each other. And, you know, you can give two people the exact same instructions and they will interpret them differently. And it's something we will like rehearse our experimental protocols to make sure we're getting the response that we expect. We pilot all of our studies before we start running experiments. So that's part of it is practicing as the experimenter, asking people what you want them to do and making sure that the instructions you're giving are clear. And then in terms of the like fidget problem, you can then also add multimodal sensors that can help you basically on the back end understand what the person was doing. So most wearable wristwatch systems will have an accelerometer in them as well. And so that's something we will sometimes use to characterize how much they were moving and use that to correct the ECG signal. And you can do that with other sensors as well. Like for the sweat problem, you could include a sweat sensor close to where you have the ECG signal, and then you can see like, oh, this person's signal changed in this way, and we can see that their sweat signal changed in this way. So now we know how to interpret that data, which is harder if you only have the one signal. I hope that answered that question.
Yeah, absolutely. I think going back to the subject question as well, you mentioned kind of offhandedly why, and I think maybe you answered this in your rest of your lecture, but offhandedly that first group of persons that you selected were all male presenting. So why were those, was it 6 people in that first initial study? Why were they all male, and what made you make that selection?
Yeah, it was 10 people, and to integrate the sensors into a garment, into the same garment, we developed an adjustable shirt, basically, that was based on design guidelines that we have of like a large study of like human body dimensions. We based it on a certain range of body dimensions and body shapes. And in order to use the same garment to integrate the electrodes, we needed to constrain that design space. It was going to be impossible to have like the smallest individuals to the largest individuals. And then chest shape became a really challenging piece, as I mentioned, with making sure the electrodes press onto the skin. And so because we wanted to do this initial characterization of the patterns and the threads and the sizes, we wanted to basically give ourselves the easiest problem possible by having the same shapes, at least on the chest, and a small range of sizes. And our rationale also is that we weren't using this study to draw any conclusions about the experimental population, which I wouldn't have made that decision if we were trying to study something like depression or stress, because it's really important that we get good representation. This was a, technology assessment, and so it was deemed that this wouldn't be impactful for society if we constrained ourselves to one sex.
Thank you. Thank you for making all those distinctions and just like slicing that in the end so well. I really appreciate that perspective. And we have a question here actually about your process. They wanted to know like what were your biggest challenges? Was funding, material fussiness, the right people, tools, the transdisciplinary exchange? Like what were the biggest challenges with this project for you? I think working interdisciplinary is wonderful, but yeah, there can be some barriers.
Yeah, I think honestly, yeah, there's a lot of joy in all the pieces that I'm reading here. So like, yes, those things are challenging, but then also were really interesting and fun to navigate. I think the biggest like annoying challenge is then figuring out who the right community is to share the work with and how to share it in a way that's going to make sense. And I think that continues to be challenging with bioastronautics work in general, because we are super interdisciplinary and we touch so many different communities that we're constantly trying to morph the work to be intelligible to another community that we don't necessarily work with closely. And I think that piece has been and continues to be the hardest for me, is knowing how to package the work and make it be perceived as impactful to different communities.
Yeah. Yeah, that's a huge challenge with interdisciplinary work in general, right? Is that like what community are you justifying this to, especially in academia, right? It's like we have to say like, oh, I'm working by these standards, but then I'm also need to impress these folks over here in this other discipline. And so how do you frame those different conversations? So
Yeah.
appreciate your insights there. Laura, did you have some questions for Katya this morning?
Yeah, so I'll open it up to my class too. If you guys have any questions, let us know. So we have one question in the class. John, do you want to share it? And I'll reiterate it if
Okay,
Katya
yeah,
can't
sure.
hear.
I was kind of curious about the technology of like there is fabric that when like powered or charged is able to flex or move in some way. And I was curious if there is if there's like an aerospace application of that like make fabric tighter on your skin or looser to maybe
Yeah.
counteract or control some of the movement variables that
Okay.
happen.
Can you hear that okay, Katya, or you want me to repeat?
I think I heard well enough. But
Okay.
yeah, correct me if I'm answering the wrong question, but I think the question was around like active materials and materials that can like hold a firmer shape if they have like an electrical charge running through them, that kind of thing.
Yeah.
Yeah, there are tons of applications in bioastronautics for that type of thing, especially for like the experimental space suits, like mechanical counterpressure suits. It's basically a really, really tight compression garment that you put on so that your body maintains pressure. And like putting them on is really challenging because they're so tight. So some folks have done research looking at, putting it on as a loose garment and then having the garment activate and basically shrink onto the body. People have used shape memory alloys for this, but I'm not aware of anyone using like kind of a shape holding fabric in that way. So I think that's potentially a cool application. Also for wearable sensing, we want some compression too to maintain contact with the body. And I think that's potentially an area where some soft level of compression that happens when it's on body would be valuable.
Yeah, I think for me, I was most intrigued by like the legacy of one material working and then iterating off that, right? Like we have data sets that have been compiled for one body, or we have these spacesuits that have worked in this kind of way. And so there's like an inertia to those. And I find that increasingly becomes present in working in textile materials because just the connectors you have weren't made for something that's flexible, or so you end up kind of encountering all these like sedimented decisions and little things that worked over time. And I'm just curious from your perspective, like how do you start a new foundation, right? Like, where do those come from, or how do we offer more flexibility in those spaces?
Yeah, that's such a good question. And I mean, I find myself running into this now as like, I'm trying to build my career and I'm like, well, I've made these woven textile electrodes and I know they worked. So like, let's keep using those. And so I'm doing it myself, right? Because it's technology I worked with and tested and I know it works. And I think I'm trying to combat that by like inviting other perspectives into my orbit. So Sarah, who's in your class, is my PhD student now looking at the textile electrodes from like a different perspective. And, I've tried to not interfere too much in her exploring this space on her own. And hopefully that will lead to maybe a parallel development path where we can still use lessons learned from what was done before, but not just be stuck in that same lane. But I think it's a pervasive challenge as well, especially with like funding structures for research where like you have to have pre-existing evidence that you know how to do the thing. So you're going to keep proposing the same thing you've been doing, and our system kind of encourages that. So I think it's hard.
Mm-hmm. Yeah, I like the prescription of a little bit of controlled chaos.
Yeah.
Or seeing like new researchers as places where that can kind of develop differently. Could be really nice. Any other questions in the class? Cool. Well, Katya, this has been so lovely. There's definitely some more suggestions in the chat, which we'll also save and we can pass it to you since you probably didn't have time to be reading it closely. But you've reminded me why collaborating is so fun. And I think we were so lucky to have you as one of our first collaborators. And yeah, I was trying to write in the chat, but like, I think what made your collaboration different too is you came into the space and were ready to absorb the textile knowledge instead of presenting a challenge and then being like, impress me, right? Like you got in there and started weaving. You were able to understand for yourself how this worked and the challenges. And I think that made the collaboration also a lot more valuable for Sandra, who was coming from the textile side. So anyway, just thank you for your kind words and your work and for sharing your practice with us today. And so excited to see how it develops and so happy to have you close, but also on a different part of campus, which feels very far away.
Yeah. Yeah. Thank you. Yeah. Thank you for having me. And I'll just say that the practice continues. I know Sarah grabbed a loom from our lab yesterday to give to somebody to learn how to weave. So we're still doing it.
Nice. Well, there's probably several people in the audience who's like, hey, if you need a weaver. So, cool. Well, thank you so much. And thanks to everyone for joining. Just another quick plug that our next talk will be on Wednesday, December 4th with Bhakti Zeek, who is one of the co-authors of The Woven Pixel, which has really been the de facto textbook for weaving with TC2s using tools like Photoshop, and also just has such an amazing history and outlook and practice that I'm excited to hear her perspective. And we hope we'll see you all again. And yeah, thank you so much. Thank you, Katya.